Hi again, my name is Mads and I'm from FlowHow. I have a quite important video here who can help you build up the correct process. And if you have the correct process, the possibility of having getting the right results out of the simulation is much higher. So in this case, I have a part here and it's like I'm starting from scratch. I have made the mesh and chosen a material, and I've chosen an ABS. It doesn't matter which kind of material. Of course, there's some differences if it's a semi-crystalline up against amorphous, but still, um, yeah, the procedure how you get to the correct process is quite similar. The first thing I'll do is I'll check the thickness of the part because then I have an idea what are the dimensions and are there any local thick areas. In this case, it's just a simple box, so it's quite easy. But anyway, I'll take thickness on this one, and I can see the top surface is 1.5 millimeter and the sides are 1 millimeter. So really simple part. This is a Moldex 2024 release 1 I'm using here, and the way that it shows thickness is a bit different from the earlier version and much better. So now I have the thickness, and to get out of this I can just click the model here. Um, I have a cold runner like this. I have a cooling channel like this, and that's it. So now I want to try to find the best possible process so I can rely on the results. So back to this tree. Um, I'll start with the process. I've done some simulation, but anyway, um, I'll put in the 5,000 bar and 1000 bar here. This is the machine settings. If you need a packing pressure higher than 1000 bar, you need, of course, a machine that can deliver higher. But in my case, I'll just put in the limit here. So the filling time. Um, the filling time I choose first is looking a bit on the part and saying, okay, how big is it? Uh, and it's not how chunky it is, but how far is the how big is are the flow lengths of from the gate. If you're more gates, of course you go a bit down in filling time. And also, if it's a cold runner, include the length of the cold runner. But small parts, if I had a part only the end here, would be 0.3 to 0.8 or something like that. Uh, Medium parts, um, it it's actually around a medium part, but the medium part is zero point 0.8 to 1.5. And again, it depends on the wall thickness also. Smaller wall thickness, faster filling. And a small wall thickness is 1 millimeter and below, so it's quite small thickness. Um, and big parts 2 seconds and higher. So I first trial here, I just choose one. I, sometimes you have an idea, sometimes you don't have an idea what it should be. And then these are just a switch over. The packing time, the packing time to be able to see when it freezes, I use the molten core for that. You need a long enough packing time. So a good suggestion for packing time is uh, the wall thickness, and that's the maximum wall thickness that you're looking at, that you are able to pack from the gate. This in second order times 2 to 3. So in this case, I have the packing time. I have the wall thickness of 1.5. In second order, that's 2.225, and then times 3, it's around 7 to 8 seconds. It doesn't matter. It's better to make the first simulation a bit longer. If you have a really big part, there will always be feeded in hot material around the gate, so you need maybe a slightly longer packing time there. But you can also use this small pocket calculator, estimate cooling time. This is just a calculator that calculates if you, for example, now it says average part thickness. It's you can't use average for anything, because the average is not something you have to wait for to cool down or pack. You need the wall thickness, actually the maximum. So, but if I put in 1.5 here, and if I start with a melt temperature, mold temperature 240 and 40 in mold temperature, I have this eject temperature, eject temperature. How long would 1.5 millimeter wall thickness from 200 cooled? How long would it take for 1.5 millimeter wall thickness to cool from 240 degrees down to 102 degrees? And then I can just hit estimate, and it says 3.1 second. And that is if you don't have, if you have perfect cooling, if you have if you don't look at the that you put in more material during the packing stage. So if I change this one, you can see it changes. But normally this will actually hit normally maybe a slightly below the packing time, but it differs. But I use back to this. I use this 7 or 8 seconds. In this case, I use 8, and then I need to refer to machine pressure and give in a pressure. I start out with quite a high pressure. In this case, 800 bar, and melt temperature 240, and mold temperature. And then I go to the cooling settings. Yeah, just put up your transient cooling. It doesn't matter if you use the general or transient. You just have to calculate it as transient. Cooling time, um, I put something on top of that. Sometimes I use the same as the packing time, but it depends on how many hotspots due to the cooling in the mold do you have. In this case, I have a quite okay cooling, so I take 6 seconds. And mold opening time, yeah, 3 seconds. It's fast to open, eject. And then, of course, the cooling, I just put in uh, you use the mold temperature as the coolant temperature. I say save to that. Yes, okay. And of course, I run this transient analysis, and I use some time steps in this. I use the fill for 9 steps and the packing for 9 steps. So I have a zero point 0.4 split with 0.4 in this case. And yeah, and the warp I used enhanced in this case. So I calculated this, and I got these results. I go back to one with where I have results here, and I go to the filling. The first step is finding out. Of course, I just look at the filling. Does it look quite okay? It does. And the first step now is defining the injection time. So I forgot here, what I normally do here is I just give it a remark, run remark, IT 1.5, packing time 8, cool 6. If I have something with melt temperature, I'll also type that in, but and then the pressure 800 bar. I'll give it like that. And I calculated this, and the melt front time was 1.5, and then I look at to define the injection time, I look at the melt front temperature. And here I want a temperature that is not decreasing too much, because then it's losing temperature, and you have the different surface temperature when the melt front um, hits the cavity wall. So you want here a uniform melt front temperature that is the same as the start of the melt. So this picture actually shows the whole filling of the temperature of the melt front at a given stage. So we start out here. It has the melt temperature is 242 because we had a bit of shear heating in the runner. And then we, when the melt moving forward, when the melt is here, it's green, it's around 234. So actually it drops down in temperature, and the longer you get away from um, the gate, the lower the temperature of the melt front gets. So um, it's losing energy during the filling, and that means that we actually mold to fill the cavity too slow. So we have to increase the filling speed, otherwise we get a cold melt front. So I take a notice that 1.5 in filling time is too slow. So I'll try with 0.5 because it's quite thin walled. If it had been 2 millimeters, it's actually not. It doesn't matter if you fill it with 1 second, 1.5 seconds. The tolerances are quite big. So I use the melt front temperature for the filling, and of course I also check check the filling pressure that is not way too high. Next step is then I have the filling time. Next step is the packing time. And the packing time, there's more possibilities. There's a flow rate in gate. You can pull out a history curve. There's a particle tracer. You can see the movement during the packing. But the easy way is just looking at the molten core. The molten core is a frozen. I'll just switch on this one. Is what is frozen. So everything transparent doesn't have a molten core, so it's not able to pack anymore. So what I do here is I right click here and have packing time, and then I can use the steps up here, and you can see now we go back in the packing time 6 seconds. It looks like this, but if I right click here I can go and say 0.8 seconds. After 0.8 seconds, we have a molten core here, like this. So the the blue area shows, or volume shows, uh, which part of what you are able to pack still, because it's still fluent, but fluent to some extent. It's still, the viscosity is still rising due to the decreasing temperature. But what I find looking for here is when we don't have anything connected to the gate, we are still able to pack this. I go down to 4 seconds. We are able to, we have a small area around the gate where we keep on pushing hot material into. So I would go for a packing time of 4.5. So I noticed that on my note block, and then we have the injection time, we have the packing time. So the next step is the cooling time. And the cooling time is when we are able to eject the part. So we need the ejection temperature, and in this eye up here, you can click here and say, ejection temperature 102. So we're looking for a temperature of 102, but be aware that we had a packing time of 8 seconds. That was way too long, because we ended out with a packing time of 4.5. So what I go for here is a cut through. I'll remove the runner because I don't need the temperatures in the runner to define the cycle time. Sometimes, of course, you do, but you don't know what the temperature should be, because you'll never wait for the runner to be totally solidified. Um, so I'll make a cut here, and you can see inside here, this is the maximum temperature. We have 68 degrees, and the ejection time was 102. So I right click again here and say, okay. And this was with the, you can see a cooling time. Here we are 11 seconds down in the cycle. And if I go to this cooling, we still are much under this one. Don't use the pack and fill temperatures. If you're using them, use them from the pack and fill results. So in this case, I don't use this for anything. The cooling results only for as initial temperatures during the packing. So I'll go for the temperature in the packing. And now you can see at the end of pack, we have a temperature of 155 in the gate area. So what if we were at the end of pack? Okay, around 92. What if we were 1 second up there? Yeah, around this. So, and in general, you can have some small areas that are too hot, but yeah, the cooling time doesn't mean that much for the results, um, any of the results. So if you're hitting one plus minus 1 second or 2 seconds, it doesn't matter on the warp results. It's only for, of course, for the cycle time in reality, that's the problem. But anyway, I say 7 seconds. We had 4.5, so I go for a cooling time of 3 seconds, around 3 seconds. It should have been 2.5 maybe, but I put on a bit. So 3 seconds in cooling time, and now we have the injection time, we have the packing time, we have the cooling time. Now we need the packing pressure. And review if the packing pressure is too high or too low. Of course, you can profile it, but then you can take a look at one of the other videos. But I go to the warp results here, and what I'm interested in is, of course, the shape of it. But anyway, that is not my at my initial run here is not my focus. It's getting the correct linear shrinkage, and linear shrinkage for this ABS is around 0.45, 0.5 to 0.65, or in that area, zero point 0.7 maybe. So, and the linear shrinkage is different from is not uniform. The linear shrinkage is just a measurement between 2 points. So in the distance, I use this distance in the results, and then I'm able to, I'll click this one, snap off, and then I'm able to measure like this, save, 0.57, that seems reasonable, save, it's too low. What about here? 0.4. So in general, the shrinkage is too low, and that means that I have squeezed too much material inside to the cavity, and I can only squeeze too much material in if the pressure during the packing is too high. So I have to decrease the pressure. So I use the 800 bar, I'll go down to 500 bar. I'll take these probes here, I can copy them, and I'll give it to this one, like this. And now I had a run here which is optimized based on the things that I have found out. So I go to this run one, and we'll start just with the from the opposite direction and look at the warp as it's just in our mind now. And I can then go to distance, and I can use the probes, probe 1, probe 2, save, probe 3, probe 4. Then I have exactly the same measuring points. 0.5, 0.6. I don't need the last one. But you can see now the linear shrinkage is different. So yeah, and it fits more the 0.65. Of course, I have some areas here, and in general, I should have ran with a small profile that was I ran in for the maybe use the packing with constant packing pressure of maybe 600 bar for 2 seconds, and then it should be ramped down so I didn't overpack this area. So now the warp or the shrinkage is okay for me, and I'll go to the filling here. I'll look again at the melt front temperature. It's here, and you can see now I with the 0.5 of a filling, I don't have uh, um, any temperature loss on my um, flow front. I start out still with the 240 as melt temperature. I still have a small increase of it, of the melt front temperature, and then I end out without any cold areas. So this is 0.5. Maybe it's a bit too fast because I bet also the no, it's actually decreased the filling pressure, because now you don't have any cold flow fronts. So it's quite nice with the 0.5. Next step is the packing. We want to check the packing, and I'll go to packing time, and then the molten core here. And you can see now I have a molten core 0.5 of a second like this. That's fine. And the cooling time, I'll try to cut. Yeah, I gave it, I can't see what I gave it, but still I have plenty of room actually up to the up to the ejection temperature. But I used I'll just see. I used cooling time of 3 seconds. Maybe you with this packing time of 4.5, you only need a couple of seconds, maybe 1.5 seconds of cool in this kind of shape, in this thickness. So yeah, okay. When you then have you're in control of your process, now I can start to look at all the results in filling, packing, cooling, warp, and think, okay, I'm uh, I'm on track on this. If you have if you don't have the correct process in the simulation, it's like reality. Then you can't rely on the results. So you have to find the process and then start look at the results. Okay, just some hints from here. See you.